Okay, in this lecture we're going to finish our section 11.7 material on the chain rule. Now recall the chain rule was giving us a technique for differentiating composite functions. So in this second part of the section we'll look at some applications for differentiating composite functions. So in this first problem we're told that the cost here measured in hundreds of dollars of producing X smartphones is given by the cost function c of x, which is 900 plus the square root of this polynomial. So as soon as we see this term, the square root of a polynomial, we recognize this as a composite function. There's a function buried within another function. So we know right away that we're going to need the chain rule if we want to differentiate. Now, in part A of this problem, we're told to find the marginal cost function. So recall the marginal cost is simply the derivative of our cost function. So remember, marginal, that term is used to denote the rate of change of a quantity, which is the derivative of that quantity. So here, in order to differentiate our cost function, and get the marginal cost, c prime of x, well, we could first differentiate the constant 900, and the derivative of any constant is 0, and then we're differentiating this square root of a polynomial. So to differentiate that composite function, we use the chain rule, which recall says that we first take the derivative of the outer function. So here we can think about this square root of 5x squared plus 4x plus 1200 as 5x squared plus 4x plus 1200 to the 1/2 power. And then take the derivative of that expression using the chain rule, or specifically the generalized power rule. So differentiating our outer function, well, we can pull down the power of 1/2 out in front of our function, and we have 5x squared plus 4x plus 1200, all raised to the negative 1/2 power. And then we still have to multiply by the derivative of the inner function, which here is 10x plus 4. Or simplifying a little bit, we have c prime of x is equal to, well, we can take our factor of 1/2 out in front, and when we multiply by 10x plus 4, distributing the 1/2 gives us 5x plus 2. And then the expression that we're left with, this polynomial being raised to the negative 1/2 power, recall is the same as dividing by the square root of that polynomial, 5x squared plus 4x plus 1200. So this would be a simplified expression for the marginal cost function. Now in part B, we're told to find the marginal cost at a production level of 200 smartphones and then interpret our answer. So evaluating this marginal cost, that is c prime at x equals 200, we have a numerator of 5 times 200, or 1,000 plus 2 is 1,002. And then we're dividing by the square root of 5x squared plus 4x plus 1200. Now, if you evaluate that polynomial at x equals 200, you're left with 202,000. So evaluating this expression using a calculator, we find that this is approximately 2.2294. But recall here that our cost function was being measured in hundreds of dollars, we were told in the problem statement. So our marginal cost is also going to be in hundreds of dollars per phone. So here, to get our cost just in terms of dollars, we're going to take this expression, multiply through by 100, since it's measured in hundreds of dollars. So we could say here, or approximately $223 if we round to the nearest dollar. We would have $222.94. So about $223 per phone. So our interpretation here would be at a production level of 200 smartphones, our cost is increasing at approximately $223 per phone. Okay. So let's look at another example. This next example is dealing with investment. So we have here an amount of $8,000, which is invested in a 5-year certificate of deposit with an interest rate of R% per year, compounded quarterly. So on the maturity date, the value of this certificate is given by the following function. So our future amount A is found by taking the principal amount of 8,000 and multiplying by 1 plus our rate, divided by 400 raised to the 20th, since we've got a 5-year deposit compounded quarterly, or 4 times a year. So recall the sort of formula that you had seen in your business math class, say 1093. So in part A, we're asked, would we expect the rate of change of A, our future amount, with respect to the interest rate R, to be positive, negative, or 0, and why? So let's think about this. If we were to make a change in the interest rate R, what corresponding change would we expect to see in the future amount A? Well, if we have a higher interest rate, we would expect our future amount to be more, since that interest rate is higher. Or the future amount would be increasing with respect to our interest rate. So here, that would correspond to a positive value for our rate of change. So here we would expect a positive rate of change, since increasing the interest rate which we were calling R, would increase the future amount A. So if we have a positive rate of change, that would correspond to an increase in the value of that positive amount. So in part B, let's justify our expectation from part A. We're asked to find the derivative of A with respect to R. So here, our function A is defined in terms of our interest rate R, and we want the rate of change. Now we can see that the form of our function A involves a composite function. It has this inner function, 1 plus r over 400, and the entire thing's then being raised to the 20th power. So making use of the chain rule to differentiate, well, we would start by taking the derivative of the outer function. So we can take our exponent 20 and bring it out in front. And when we multiply by the 8,000 that we already have in front, we would have 160,000 times our inner function, 1 plus r over 400, now raised to the 19th power. But we still have to multiply, using the chain rule, by the derivative of that inner function, which here is just linear. It's 1 plus r over 400, so our derivative is just the slope of that line, 1 over 400. So simplifying a little bit, we would have our derivative, let's maybe call it A prime, would be, well, our 160,000 out in front multiplied by the 1 over 400 on the end leaves us with 400. And then we still have the 1 plus r over 400 to the 19th power. So this would be our expression for the derivative of the future amount with respect to the rate r. And as we expected in part A, we can see that this expression would be positive. Now in part C, we're asked to find and interpret the derivative of A with respect to r at the rate r equals 2. So taking the function that we had in part B, that is A prime, and plugging in r equals 2, we would have 400 times 1 plus 2 over 400, all raised to the 19th. Or simplifying a little bit, 400 times 1 plus 2 over 400 is the same as 1 over 200, all being raised to the 19th power. So evaluating this using a calculator, we would have approximately $439.76. Now we're taking a derivative, so this would be the future amount per change in r, which was a percent. So our interpretation for this value we could think of as follows. If we currently have an interest rate of 2% per year, compounded quarterly, then we would see an increase in the future amount of approximately $439 or $440 if we were to increase our interest rate by another percent. All right. Now the last part of our section deals with something known as the marginal revenue product, which is a concept from economics, and it makes use of what we've been talking about with the chain rule. So here we can make use of the chain rule to find a formula for the marginal revenue product, which again is this economic concept that will be used to approximate the change in revenue when a manufacturer hires additional employees. So let's think about how we can derive our formula for this marginal revenue product. So we're starting with the fact that revenue is equal to the price per unit, P, times X, where X is the number of units that we're producing. So here, this expression for R is the total revenue for the daily production of X units, where we're selling these units for a price of P dollars per unit. So you take the number sold times the price you were selling them for, that gives you your total daily revenue. Now, the demand function is given by P, the price, is equal to some function of X. So here we can think about price as being determined by the number of units produced. Now, we can also consider X, that is the number of units produced, as a function of the number of employees, which we're going to denote by N. So naturally, the more employees that you have, the more production you can accomplish in a given day. So since our revenue, R, is given by P times X, and therefore P depends on the number of employees. So since price was dependent on X, and X was dependent on the number of employees, that means price is dependent on the number of employees. And therefore we can consider R, the revenue, as a function of the number of employees. So the question of interest is, what would be the rate at which our revenue changes, that is the derivative of revenue, with respect to a change in the number of employees. So here, if we were to make use of the product rule for derivatives using the function r is equal to p times x, the product rule says the derivative of r with respect to n would be found by taking the first function times the derivative of the second function, dx dn, plus the derivative of the first function in our product, that is the derivative of p with respect to n, times the second function in our product, x. Now, making use of the chain rule, the derivative of price with respect to the number of employees could be thought of as the product of the derivative of price with respect to total output times the derivative of output with respect to the number of employees. So remember, this is just the Leibniz notation for the chain rule. We can think about these derivatives as fractions and think about canceling that dx expression on top and bottom. So now, taking the expression which we just found for the derivative of p with respect to the number of employees and substituting it into the expression that we already found in our previous equation, we have the derivative of r with respect to n, the number of employees, is p times the derivative of x with respect to n, plus the value of x times the derivative of p with respect to n, which we just found as the derivative of p with respect to x times the derivative of x with respect to n. So from this expression, we see that there is a common factor of the derivative of x with respect to n. So if we factor that expression out, we are left with p plus x times the derivative of p with respect to x. Now this expression which we've just found, which is the derivative of revenue with respect to the number of employees, is referred to as the marginal revenue product. So in this last example, we are asked to find the marginal revenue product for a manufacturer with 5 employees. So the current value for n, the number of employees, is 5. And the demand function is given by p equals 210 over the square root of x, and x is given by 45 times the number of employees. So each employee can produce, say, 45 units per day. And then we're supposed to interpret our answer. So using this expression, which we've just found for the marginal revenue product, the derivative of r with respect to n is given by p plus x times the derivative of p with respect to x times the derivative of x with respect to n. So we have the following. Our demand function said that price is equal to 210 over the square root of x. Then we're adding x times the derivative of p with respect to x. So a little scratch work to the side here. P was 210 over the square root of x, which is the same as 210 times x to the negative 1/2. So the derivative of p with respect to x, using the power rule, is negative half of 210, so negative 105, x to the negative 3/2, or if we prefer, negative 105 divided by x to the positive 3/2 power. So that gives us, for this term, negative 105 x to the 3/2. And then on the end, we're multiplying by the derivative of x with respect to n. So here, x in terms of n was 45 times n. So taking that derivative, we just have 45. So now, simplifying this expression, we're left with 210 over the square root of x minus, when we multiply our x times negative 105 x to the 3 halves, well, my x to the first divided by x to the 3 halves, I can cancel 1 power of x. So subtracting 1 from our exponent 3 halves, we're left with 105 over x to the 1 half, or the square root of x, still being multiplied by 45. So now, inside of our parentheses, we have 210 over root x minus 105 over root x, which gives us 105 over root x times 45, or 4725 over the square root of x. So this is a general expression for the marginal revenue product, and here we were given the specific number of employees was equal to 5. So if n is equal to 5, then x is given by 45 times n, so 45 times 5, which is 225. And substituting that expression for x into the marginal revenue product that we just found, we have the derivative of r with respect to n is 4725 divided by the square root of x, which was 225. So square root of 225 gives us 15. And then 4725 over 15 gives us 315. So this is the value that we're interested in. Now, an interpretation of this expression would be if there are 5 employees, our daily revenue would be increasing at a rate of $315 per employee. So we can think about this, if we include units, as $315 per additional employee. So our revenue would be increasing by $315 if we hire an extra employee from the current 5. Okay.